We now consider the Lewis structures of molecules that have more than one central atom. So we will start by considering having you draw a correct Lewis structure for the formula C2H6O. So in this case, there are 2 carbons and 1 oxygen. All of them form more than one bond, so based on what we talked about last time, all of them are going to qualify as central atoms. Obviously, the hydrogens are not. So we're going to choose to put a carbon as the central atom because it's going to form 4 bonds. Okay, so we'll draw a carbon and make sure we draw 4 bonds to that carbon. One of those bonds will have to go to the other carbon, and another will go to the oxygen, and then the remaining 2 will have to go to hydrogen. So there are no other options. So our general strategy is we want to draw all of the atoms that form more than one bond first, and then we want to add hydrogens and or halogens around the edge of the molecule because those are the atoms, the elements that only form one bond. Okay, so following that strategy, if we add the remaining hydrogens, 3 onto the left-hand carbon and 1 onto the right-hand oxygen, we now have each carbon forming 4 bonds and the oxygen forming 2 bonds, so they're all happy. And then the last thing that we have to do is add the lone pairs to oxygen, because as we saw in the last lesson, a neutral oxygen is going to have 2 bonds and 2 lone pairs. So we add that lone pair, and that gives us a completely correct Lewis structure. Moving on, this brings us to the topic of isomers. Was the structure we drew the only possible structure with the formula C2H6O? The answer is no. I could have also drawn one with oxygen as the central atom and carbon on either side of it. This compound, organic chemists would give it a different name. It's actually called dimethyl ether. But these are examples of isomers. Those are molecules that have the same molecular formula, but different structures. And these are going to be really, really common in organic chemistry. So one way that we know that they are different molecules is that they actually have different physical properties. So we're still going to study boiling points in the final unit of this course, but for example, ethyl alcohol, which is the first structure we came up with, is a liquid at room temperature with a boiling point of 78 degrees, and this structure, dimethyl ether, is a gas at room temperature with a boiling point of negative 25 degrees. So furthermore, these isomers are also called structural isomers. That's going to distinguish them from a different type of isomer called stereoisomers that we're going to see later in this unit. And some books are going to refer to structural isomers as constitutional isomers, but I actually like the term structural isomers. That simply means that they have different atomic connectivities. Okay, so there are no more isomers. There's only these 2 possible structures for the formula C2H6O. But as molecules get larger, especially molecules you see in an organic course, there will be many more structural isomers available for a particular formula. So now I want to go over a couple more examples that are going to be a little more difficult, and as we're going to see, they're actually going to require multiple bonds in order to get a correct Lewis structure. So to bring us into this topic, we will consider the formula CH2O and try to come up with a Lewis structure for this. Well, we'll make carbon the central atom, but we only have 2 hydrogens and 1 oxygen. There's only 3 other atoms in this molecule, and carbon needs to form 4 bonds. Okay, so we have a problem here. Well, the way that we can solve this problem is to form a carbon-oxygen double bond. And this solution, so just simply draw 2 lines, have 4 electrons between the carbon and the oxygen. We'll talk about exactly how this works more later in this unit. But this solution will also satisfy oxygen's need for 2 bonds. Because in the initial structure I drew, oxygen was only forming 1 bond, and we know that oxygen needs to have 2. Okay, and then just like in the last example, the final step is to add the 2 lone pairs to the oxygen to get a correct Lewis structure. Don't forget that step, otherwise oxygen only has 4 electrons around it and not 8. Okay, our next example is C2H4. 2 carbons in this case. So we're going to need to bond them together. And, both of them are going to qualify as central atoms. They're going to be essentially identical. Okay, so here's 2 carbons bonded together. And if we just used a single bond between the carbons, we would need to add 6 hydrogens around the outside of the molecule to satisfy each carbon's need for 4 bonds. But we don't have 6 hydrogens in the formula. We only have 4 hydrogens. So just like in the last example where we did not have enough atoms to give everything single bonds, a carbon-carbon double bond will solve the problem. Okay, so this is our correct Lewis structure here. Carbon-carbon double bond, and then each of those 2 carbons is bonded to 2 hydrogens. So each of those carbons is forming 4 bonds. Remember, count the double bond as 2 bonds when you're counting up numbers of bonds. So as a general rule, again, this is applying to organic molecules, but for molecules containing just carbon, hydrogen, and oxygen, you need 2n plus 2 hydrogens for every carbon in order for all the bonds to be single bonds. So in the first case, we had C2H6O. So N is 2. There are 2 carbons. 2 times 2 is 4, plus 2 is 6. So you have 6 hydrogens, and you're okay with everything forming single bonds. In this case, we have only 4 hydrogens for 2 carbons in example 2, and 2 hydrogens for 1 carbon in example 1. So we only have 2n hydrogens, not 2n plus 2 hydrogens, which means that we need a double bond. Okay, final example, C3H4. So now I actually have 2n minus 2 hydrogens. So what do you think that requires? A triple bond, or 2 double bonds. Okay, so let's see, C3H4. Let's start with the carbons and get the carbon connectivity right. So having all single bonds for these 3 carbons would actually require 8 hydrogens, but we only have 4. So let's insert a triple bond between 2 of the carbons. The central carbon is now happy. It has its 4 bonds. The right carbon is going to need 1 hydrogen, and the left carbon is going to need 3. We have 4 hydrogens to assign, so it will work. And there is our Lewis structure. Left carbon is forming all single bonds, 3 to hydrogen and 1 to the central carbon. You've got the carbon-carbon triple bond, and then the carbon at the right side of the triple bond gets 1 hydrogen and still has 4 bonds. Notice in these structures that don't have any oxygens, I'm not including lone pairs because there are no lone pairs to put on when you have just carbon and hydrogen. Now, what about that 2 double bonds in parentheses? Could we have done that? Yes. In this case, the carbon connectivity will have a double bond between each pair of carbons. So the second central carbon is actually participating in 2 double bonds. The central carbon is forming 4 bonds, so 2 bonds to each of the 2 terminal carbons, and then each terminal carbon is forming 2 bonds to the central carbon. So what that means is each of these terminal carbons needs 2 hydrogens in order to be happy. We have 4 hydrogens to assign, so we can put 2 of them on each of these carbons, and everything's going to work out great. Okay, so that's our correct Lewis structure in the box. So you can do many, many, many more examples of molecules like this. You can make up formulas and come up with Lewis structures. And when you go on to study organic chemistry, you're going to be dealing with many more similar problems, including those containing larger molecules.